Hello everybody, my name is GrabBG and today we're going to continue to check out Java's bytecode. So I've done a little bit of work since the last time we left off. I've cleaned up some of the source code and I've actually done a little bit of refactoring. So I did keep some stuff. I will go through and explain through most of the changes, but basically, right, I made the following convention, right? So first of all, let's run the program and check out what it does, and then we can step through all of the instructions and see what happens. So, right, we have a lot more logging than last time, right? I added a little bit of logging, and I'll explain what we're going to do in a little bit later. So we're doing similar stuff to what we did last time, except now we're actually logging the constant pool, not just the count. We're logging the interfaces, not just the count of interfaces, the fields, and the methods, and also the attributes, right? So the first thing we probably need to go through is kind of step through our plan, right? So we have the path to the class, and then we open it and read over its bytes into a vector. And at that vector, now, instead of being parsed at the level of the main function, is now parsed at the level of the Java body. It has a method code from bytes, which you see in a minute is going to be something that's going to be a recurring concept. Right, so we kind of know the basic idea that this is going to give us the Java body. But then we have a condition that checks that if there's anything left of the bytes, that means that this entire thing is invalid, right? So it's not a correct thing, and we need to exit with 1. And then we just log it, right? So we've done that, and logging happens here. Okay, makes sense. Let's go through to bytes, from bytes, and from bytes it's pretty simple. So as last time, we create a default Java body, right? We have a default Java body. Then we read the U32 for the magic number, which we should actually assert is probably, or maybe not assert, or maybe yeah, let's assert it. So that the body magic is equal to 0x cafe babe, right? And yeah, that's what we're asserting. And then we have the minor version, right? So that's from last time again. If we open up the docs, right? If we open up the docs in the documentation, it says that the magic number, if we search for magic in the fourth, I think the fourth segment or chapter in this case, and the magic should be equal to cafe babe, right? Cafe babe. I just have it with lowercase. You can always just make it uppercase, that doesn't matter, unless, yeah, the X has to be lowercase, but as you can see, we have that. Then we have the minor version, the major version, as last time, constant pool count, yada yada, but now, as you can see, we're doing constant info from bytes, so that's probably similar to what we had before, but we basically parse now the constant pool. We push some stuff into the constant pool, which if you're new to this, which you definitely should watch the first video, the constant pool is basically the place where the Java bytecode stores all of its constants. And a constant can be anything from a function name, which is marked as UTF-8, a string, or a method, a class, an interface, anything. Anything goes. That goes into the constants. Then we have the access flags, which the access flags tell us a little bit of like information about what the actual core class is, right? Because every single class file has a class inside of it, and the access flags generally tell us information about it. Then we have this class, the superclass, which access flags is a little deceiving, but that's for if it's public, if it's private, protected, etc. And then you have this class and the superclass. So this class is actually just an index into the constant pool, which, as you see in a minute, isn't a exact definition, because in the index inside of a constant pool, in this case, in this constant pool, is a little bit weird. So then we have the interfaces, which are basically another just array of indexes, I guess, inside of the constant pool. And then we have the fields, which are just field infos of bytes, right, from bytes, which if we go into the function, is essentially this, right? It creates a default result, then it reads the access flags, the name index and descriptor index, the attribute count, then also the attributes, right? And then we have the method info, which is again just from bytes, method info. It reserves some count for the methods, and then we have attributes, which are the same attributes that you had in methods info and in field info. Also, these two structures are very similar, right? Very similar. And then we also have the attributes for the actual class itself. And then here's the logging from last time. I've kind of separated it out into its own section, but you can definitely just uncomment it, and that will work, right? So what's new from last time? Well, I kind of added a little bit of printing. So we take in the formatter, and then we print some stuff like the magic, the version, and then the constant pool has a function called const pool log, which logs the constant pool, right? And then you have the fields, which are also logged, methods, which are also logged, attributes, which are also logged, right? And attributes have a little bit more parameters. Generally, we just take in the formatter, but in this case, we also take in this, because this is kind of important, right? This is kind of important because we get the amount of tabs, and also we get which attributes we're talking about. So this function is kind of different from these functions. Like, they're a little bit different. They're not exactly the same. And then each element inside of the constant pool table has this method called log, which the method log just basically writes that thing, accepting the constant pool as a non-mutable reference, which is very important, because then we are able to recursively call this log function. And when do we need to call this function log recursively? Well, in this case, for example, for string, right? The string index actually has the string itself has a string index, which is an index back into the constant pool table, right? Where we have the string and we have the actual UTF-8 that represents it, right? It's just a different type, right? It's a different type that just references this type. And then, I mean, you already probably see it, but indexes inside of this table, like, they're a little bit weird, right? It has all gotten a little bit out of hand because the indexes actually start from 1. So you would get, like, if you wanted to get the first element, you would get at index 1, not index 0. So what we just do is just string index -1, and then interpreted that as the usize, and then we get the element, and then we log it. And we have a little bit of info, which is actually like how most of the time we do logging, where we give it some names, and then if it has attached data to it, like for example this, and here has method ref has a class, and then a name and type, right? So we log that this is in fact part of the method ref, which is called a class. Part of the method ref, we have a class, and that class is this. We log it, and then this log, this log. Also, if you're wondering, this is actually a way to write this inside of the formats, because right, this is for if you wanted to print a variable. So to escape this, you just repeat it twice, right? So this actually results in this, just as a quick reminder. So right, we have really basic stuff already implemented for logging, right? But one thing we definitely need to check out currently are attributes, right? Because if we just clear again and run the program, what do we get? Well, in here we have methods with some name and type, and that doesn't matter, right? Constant pool is just where we keep all of our constants, so we can probably kind of ignore it, because we're more interested in the methods, the fields, and the interfaces that reference that part of the constant table. So we have the method info, right? And it has some attributes. And it's weird how methods have an attribute called code. And as you can see, this is actually a common occurrence. And even the class has some attributes, like for example, SourceFile, right? That's interesting. So actually, attributes, if you remember from last time, if you go to attribute info, right? It has an index inside of the console pool table for the name of the actual attribute. And then it has some bytes, right? It has some bytes, which in the previous video we kind of overlooked or mostly ignored because we wanted to just parse kind of the file, but now they're a little bit more important, right? They're a little bit more important. So now what we can probably do for today's video is actually finish logging, because currently what's being logged is actually, if we check out logging for the attributes, which I don't do, oh well, I guess I do them here. So we have F, which just kind of we're writing some padding, an open array of some padding, which is here. We don't really care about this, like you shouldn't really caring about this, but this is just for formatting so that it looks kind of cool, like you can see, as you can see here. But basically we have this, right? And we take we iterate over all the attributes that are given to us as a parameter, and then we just log their name, right? We don't log their bytes for now, right? We don't log their bytes for now. So how about we actually log that? Right, that could be kind of cool, I guess. Let's add a comma, and let's do something like, I don't know, info, right? Because info is called the thing. And let's actually log them as debug, right? And that's for what? For attributes info, right? So let's see what we can get. It's not going to look like a total mess, but okay. So we have some attributes, and in here we have SourceFile, which just has 2 bytes, some sort of info, which is interesting, right? Something to keep in mind. And then the code has a lot of bytes. Could that mean that inside of the code section there's actually code? Well, yeah, it's kind of implied, right? So there is actually code in here, but we haven't really parsed this section just yet. Coming back to SourceFile, as you can see, we have 2 bytes. And if you've done anything with Java and stuff, or if you've watched very carefully, as you can see, indexes in this case are all U16. And how many bytes is U16? Right, 1 byte is U8, right? 2 of U8 is 2 bytes, which is U16. So SourceFile has 2 bytes, which are the actual reference to, maybe it's like an index to somewhere. We're not sure, right? We're not sure. But what if we know that by looking into the constant pool table? Like, let's imagine this. Let's actually count how if this was an index, right? If this was an index, where would that be? So this is big endian format, so that's the first byte, and then 0 we ignore it, right? So this is the first byte, so that would be 0014, which is 14. Oh well, I've muted myself and I've been talking do nothing for like, what is it, like 10 minutes. Okay, so we have the name, right? And I guess for now let's just log it. We can go through the steps explaining what I'm doing. What have we been doing for the past, I don't know, however long I forgot to mute. So we have the attributes, right? And we were essentially just refactoring stuff away, trying to make it easier for us to parse it, right? At the level of like parsing, right? We're parsing them and the bytes are getting transformed into actual readable stuff at the level of parsing, right? Or at least it's stuff that Rust can understand, right? So now we're here and let's just log it, right? So we have, I guess, yeah, that, and then I guess for this we can do what? Well, we can return a reference to vec of view, but that doesn't matter. Alright, so that should actually return. So no, but it can actually be an option to like a reference of vec of u8 self, I guess, in here bytes. Let's return a byte, some bytes. Okay, that worked. So now we have the bytes from bytes. Okay, and let's actually convert them to UTF-8. So the conversion from that to UTF-8 was just a case of doing this. So sure, where was it to do? Right, that makes sense. And that's the name, right? So name a slice expect code, right? That was code. So we've reached the point at which we have to parse the code. So now we're looking at what code is, right? So a lot of stuff, definitely a lot of stuff. So for now, we could just do something like very primitive, which is just info vector of u8, right? So then you just do bytes, so read bytes length bytes, and then we just get info, so just return. I guess we can just match them, right? So that's, we can just do something like, okay, match is this thing we're talking about code, right? So we expect that it's a UTF-8 string, and in case it's code, that would mean we just read the bytes and we just return self code, right? So that's it, and info is equal to this, right? Kind of makes sense, right? And let's not put a semicolon here, otherwise we can actually panic saying unknown name of attributes this. I guess we can actually just do something like override the name itself. So let name equal to name, so we just do name unknown name of attribute name, so attribute name. Alright, so that's our code done. Okay, so it's backwards, right? So it's from the bytes we read length, so that's the amount of bytes. So that's as you say. So now we have an unknown attribute called SourceFile. And then we just go into here and we do SourceFile. Right, and let's actually implement SourceFile. Let's find SourceFile. Attribute is an optional fixed length attribute in attributes table class file. This can also be no more than SourceFile attribute. I don't. Right, yeah, that's SourceFile index. So this stuff we already have it parsed, and now we just need the SourceFile index. So that's exactly what we saw earlier, right? We were reading all of the constant, the IDs, right, of all the attributes and all the informations about them. And we found SourceFile with 14, which pointed at the actual place at which the UTF-8 string that stores the actual path is located at. So that's probably going to be SourceFile, I guess, name, which is a U16, which is just a pointer or an ID in this case into the constant table. So that's self SourceFile, that's name, which is going to be read U16 of byte. Right, so that's it. That's essentially all we're going to do, right? We're going to read the bytes, but we're also going to assert that length is equal to what was it? Standard memory. I think standard, we could just write, like, we can write 2, but what if SourceFile changes, right? Imagine this. SourceFile changes. How can you actually do this more efficiently? Right, SourceFile changes. Now you have to go to assert and change that. And then if something else relies on a certain size, then we have to change that as well. Right, and you have to remember to change that. And that's very annoying, right? So instead of that, what we can do is actually use standard memory sizeof. Alright, sizeof. So that just returns the size. So we can just do standard memory sizeof. And that's going to be self SourceFile. And let's see if it compiles. So it's actually assert macro, right? It's an assert macro. And I guess this we can convert to U16, since Laurent is actually this U16. We can say error source file size did not match Since we're just doodling around, this doesn't really matter. I guess that's it. COS. Cannot. Oh, right. So that's U32. Size of not a value. Expected argument. Help remove extra value. Self source file is not a value. Right, let's actually see the documentation for this. Aha, okay, so that makes sense. You provide it as a type to a template, and then that. Yep, makes sense. COS, right, so that's size of, and then this. That's kind of cool. So, expected type found variant source file. And remove the semicolon also, yeah. Okay, so we have this for variants. Can we do size of variants? Size of. Example for unions. Well, I guess we can't really do this, right? That's kind of sad. For now, we can just say, okay, that's 2 in U32. So that should be our source file, parsed, right? Except that now logging doesn't really work as expected. Right? Logging doesn't really work as expected. So now we can actually go into here, into the methods that parse this kind of stuff, and we can do something like attributes log, right? We do attributes log, we get the attribute, and then we log that. So how about we now do something like write f body, and that's going to be, and that body is going to actually be the attribute log. And what are we logging? We're logging into self constant pool, we definitely need that, and then the formatter, right? That's it. But as you can see, we don't really have this function, right? There's no method called log. So how about we go to enum attribute, right? And let's actually implement this function. So we need to do log, right? And that's constant pool, which is, I guess we can just call it a pool, and that's going to be a reference to a vector of constant flow, right? And then an f, which is called just a standard formatter, which standard formatter is this abomination. So we have that, and that can actually error, which we have to now add this, and it's so annoying. I can't even begin to describe it. So we need to do this, send an empty result, and then we need to return okay with empty braces, and that's fine. Okay, finally we're here, right? So we're logging the body, right? So we should do something like, okay, let's match our self, right? Because we're taking in self. Right, well, let's match ourselves. What are we? Are we self code? Well, in that case, we can just kind of just log the actual bytes. So that's just f. I guess just bytes for now. We can just do something like code space and then bytes, right? And that's it. And then self source file. Are we a source file? Yeah, let's actually get the ID. And let's do write f source file, which now we should probably log the actual string for thing. So now, well, we actually have a special macro for this. Not macro, but the method log, right? So we just do pool get id -1 dot expect invalid index, right? And after that, we just do log with the pool and the formatter, and that's it. And that can fail, and we just, in that case, check if it fails. So now we have this implemented, and what do we get now? Right, yeah. So that's actually called info. And for this it's called info. For this it's called name, right? So name. And now if you run this, we also have bytes where, yeah, this should be info. Come on. Oh my god. Okay. So you have that, and now we need to convert it to i16. So let's do something like e as usize. Right, that's it. And now we have, okay, so kinda, right? So now in body, on the body space, right? Here we also should add a comma and then a space. That's probably gonna make logging a little bit cleaner, right? So now we have the source file, which is a UTF-8 string called hello Java, right? Right as we checked it. exactly as we checked it, right? We have hello world.java, right? That's kind of cool. Now all this cool stuff, but we still haven't parsed the code, right? And the code is probably one of, if not the most important attribute of all, right? Because it stores our code. So how about we actually parse it? So the way we do that is just code info, or probably code attribute, right? Right? Okay, and now we have this attribute. And let's actually do this. So now with this structure, it would probably be very much useful if we did something like size of variant in Rust. Oh, I want to do something like get size of variant. What's the biggest variant in an enum in Rust? I don't care about that too much now. Okay, let's just do this without it. So let's go to our attribute, right? Attribute enum attribute, right? That makes sense. And in here for the code, let's actually paste this. We can then do something like this, and then we can just tap this in, probably from the start. So here, probably without the extra space. So that's it, right? And let's actually parse it, right? So we can get the name itself. So I don't know. Oh, right. So these two fields we kind of ignore. We already have them, right? We don't really care about them. So now we can actually get the max stack, right? So now we have the max stack, which is a U16, right? And I have the max locals, which are also a U16. That's probably not going to be what we want. We kind of just want the code itself. So because inside of a vector, the length is stored, right, instead of a variable. And there's going to be a vector of U8. And then we have the exception table. Exception table length. Which, again, we probably want to just have the exception table. Exception table. Which is, again, a vector of exception of this stuff. So that's actually an exception, right? Let's actually define that. Struct exception, I guess probably code exception. So code exception is actually going to be start PC, which is U16, an end PC, which is a U16. We have the handler PC, which is another U16, and a catch type, which is another U16, right? And that's the code exception. Code exception, right? So that's the exception table, and then we have the attributes, which are just, I guess now we have to actually kind of recursively have that, which is, no, we don't, right? We have the attributes. We don't have to have that recursively, right? Attribute info, right? Makes sense. So yeah, right? So we have that. We have the attributes, and how about we now start parsing it, right? So we now don't have the info, right? We have a lot of other stuff. So let's form this. So max stack. I guess we can actually probably do something like self code default, code default, which should just return a self, and that would just be a code one. But I guess we kind of need to abstract this away, so we can actually probably make its own kind of thing, so kind of structure, right? So that's code block, and that's actually going to have all of this stuff. So just take this, delete it, code, and that's going to be a block called a code block, right? And instead of the code block, we have this, and this is essentially just this, right? Attributes, exception table, and all of that stuff. And this can now probably derive default, hashtag derive default, and we can now do this, right? So we can just do code block, I guess let block equal to code block default, right? So now we can get the block max stack, and that's going to be equal to read use 16 bytes, right? And then we have a block max locals, which is also going to be read use 16 of bytes, right? And you probably need this to be okay, right? We have block code, which we now need to get the code length, which is going to be some variable, right? So let's code length equal to read u32, right? That's bytes. Okay, and that then going to be our code. So then we do block code equal to read bytes of code length, right? As you saw, probably. And then we can actually do something like exception length, right? So that's a read u16 of bytes. Okay, and then we can just actually get the exceptions. So now we need to do for I in, I guess, 0 in 0 to exception length, right? And that's going to be block, I guess, block first reserve exception length, and then we have block exception table dot push an exception, right? So called exception, which is going to be a start PC, or probably worth just putting it in its own function. I don't know how it would be useful, but maybe it would be. So let's actually just do that. I don't see a problem following an actual like structure that we established already. So from bytes, and that's just going to be bytes mutable vector of u8, and that's going to be itself, right? Well, not for code block, but for code exception. Right, so that would be just self with read u16 bytes, read u16 bytes, read u16 bytes, yada yada, right? And now we just do that again and again and again, and that's start PC, end PC, handler PC, and catch type. And read u16, right? That's it. And then from the code exception, right, we parse that, we push it into the exception block stuff. Which I guess, now that I really think about it, if we want to follow our structure, we probably should just have a function like from bytes, from a method for creating code blocks out of bytes, right? So fn from bytes mutable vector of u8, and that's going to return itself, right? So that's essentially going to be what we're doing here. So that's block exception table and all that stuff, but we as the end user don't have to bother about that at all, right? We don't have to bother about that. So we're just going to open the block. And what else does the block need? It has some attributes, right? So we need to do array length, array count, I guess, which is going to be a read u16, right? Bytes, right? So now we have the array count, so that's the attribute count, and then we can just do for in 0 to attribute count, right? We just do block attributes after we reserve again attributes reserve array count attributes push. And what are we pushing? We're pushing attribute info from bytes, right? That makes sense. What doesn't make sense is the inconsistencies, right? Inconsistencies in the Java bytecode, right? So you have lengths, which are also the exception. Length is a read u16, right? But byte lengths are u4, right? Or u32 again. And code is right made of bytes. That makes sense. And then you have the exception table. But what doesn't make sense is the fact that length is now 16 bits. This is 32 bits for bytes, and this is 16 bits for length. Why not just make all of them 32 bits? Or all of them 16 bits? I don't see a world where code length is going to exceed like the 32-bit limit, I guess. Which could make sense, right? But I don't think that's how you should design your APIs. So anyway, right, we're getting all the attributes, right? So we have that. And I guess a simple verification check for size is probably definitely needed. And that just returns a use size. And that should just return. So that's 2 plus 2 plus 2 for the call. So that we have no, plus 2 plus 4 plus the length of the actual code. So that would be self code length plus the exception table count, which is 230. Yeah, so that's, yeah, right. So okay, 2, and then the length, and then yeah, okay, code length, and then we have the exception table count, and then the actual exception table, which would be self code, I guess, exception table length times mem sizeof, and that's attribute info. But then attribute says their stuff. So I guess for now we're not doing verification, right? We're just going to leave this to do verification. Right, it's too much work for right now. I'm going to probably end up doing it off camera. Right, but right, we got this working, which is, I guess, kind of cool, right? We're parsing the code now, and then right, this in here we're supposed to actually do self code, right? So now we have block, which is self code block from bytes, or it's not self, right? It's just code block from byte, and those are our bytes, and that's kind of it. Believe it or not, that's kind of it. We're still missing the size verification, but that doesn't bother us too much. We're kind of assuming it's correct. So that's it. Right, so let's get this. Right, now we're experiencing some errors. Line 175 bytes, right? That makes sense. COS, and now what do we have? Exception length as you said. and this as usize, right? That all makes sense, right? That should make sense to you. And then from bytes at 184, and that's what we need. Also the pool, okay. Well, I mean, we can pass it in here, so that's vector of const info. Just call it pool, I guess, yeah. Okay, so now we have that. Cannot be formatted using hashtag debug. I guess we can just drive debug as well. First of all, COS, and now at where 165 code exception. Well, that's why I didn't really want to do this, but it's fine. Drive debug. Now we have from bytes, which I guess now we can actually pass at 170. 170, okay. 206, right? 203, not 206. From bytes also requires pool. Makes sense. COS. Okay, and now to the error where we have info instead of block. That's just block, and I'm too lazy to implement logging right now, so we just do block. Right? This should work. Unknown attribute linear line number table. Interesting. So that actually arose as an issue in here. Right. If you enable backtrace, you would probably see that it arose in here after getting another attribute. So now we're getting into the deeper territory, right? We have line number table. And how about we implement that? That doesn't seem too bad, right? And that doesn't seem too bad at all, right? So we just do, where is it? Source file here, and we just do line number table, right? That's another attribute. And then we just search for line number table attribute. Right. Alright, so now we have this. Okay, and we now can actually describe this. Add something. So it doesn't seem too bad, right? We definitely could actually abstract this away. So let's do something like line number table element, probably, because we need this to actually define like start PC, which is U16, and then line number, which is another U16, and that's going to be a hashtag drive debug, right? So that we're able to print it. And then we do so that's just basically a vector of line number table elements. Make sense? Should make sense, right? And now we actually need to implement this. So that's line number table, which should be pretty easy to implement, right? So you do length, yes, line length, which they call it length, but it's actually count, right? And then you read you 16 bytes, right? And that's the count. And then we can do something like let body equal to a vector new, which is actually, this is going to be a vector of line number table elements, which in this case we actually call it a body, probably. I guess a table. And then for 0 to line count, from 0 to line count, we can kind of just read all the stuff and collect them into the body. So we do, even we can now do with capacity, line count as usize. So now that's a little bit more efficient, right? So then we do body push the line number table element, line number table element, and again you should probably make a function for parsing it to bytes, but that doesn't matter to me right now. I'll do it probably in off camera. So that's line number, which is going to be another read 16 bytes, and that's it. That's simply it, right? So then we push, and then we just return self line number table, which is going to be a table of body. Make sense? Probably should make sense. So not covered in 239. Okay. Self line number table. That's our table, I guess, in this case, and then we just do write f stuff, write f, that's line number table 2, and that's going to just be, I guess for now we can just do something like table. Right, that's pretty simple. And okay, right, we parsed it. So it's probably quite big in terms of size. So how about we actually probably pipe this into debug.log and check out what the logging is. So debug.log, right? And what do we have here? So this is kind of the constant pool, right? And then we have this. So we have a code attributes, which has a body, which is a code block. Code block. We don't really need that information, right? We already know it's a code block. So then we can actually go like this, as a max stack of 1, and that's for init. We're probably not going to be going into init, right? But yeah, that's pretty fun. Attribute name and index, and some attributes. That's kind of cool. So then we'll just do method info, and here that's the main function, right? And we have a max stack of 2, max locals of 1, a code of this, and then the exception table of this, and then some sort of attributes, right? It has an line number table that we kind of don't care, right? We don't really care about this part, but we've parsed it, right? So that's kind of cool. Alright, let's clean this up a little bit more, right? And that's it. So we've got this, which can now be parsed, right? And now we're getting deeper and deeper into the attributes, right? Next attributes inside of code, I guess we probably want to actually parse the code into actual opcodes and log it correctly. But for right now, I should actually be able to find that attribute, right? So that's it, code attribute, right? And we have code, which code is an array of actual Java machine code bytes that implement that method. When code array is read into memory on a byte addressable machine, if the first byte of the array is aligned on a 4-byte boundary. The table switch and lookup switch 32-bit offsets will be 4-byte aligned. I refer to the descriptions and the consequences of array. Called array, I don't really care. The detailed constraints of the contents of the call array are extensive and are given in a separate section. Oh my god. Okay. So, right. We have a lot of stuff to check. So, how about we actually go back again. Now that we've actually parsed kind of like the entirety of the attributes, we should check out probably where is it? Type of instructions. And there's a lot of instructions in here. Verification of type, loading, linking. Can I actually check out the instructions? Right. Thank you. Okay. So, and what is actually like? Yeah, the Java instruction set. And the instruction set consists of the opcode specifying the operation to be followed by a 0 or more operands and modding the values upon the operator upon the character. Whatever. The description of the instruction, the content of the Java machine, the static is constraint, structural constraints, structure constraints. Code is specified in an array. There's a bunch of constraints that I don't really care about, but yeah. So it's a mnemonic and then an operand 2 and an operand. Okay, operand 1 and operand 2. Yep. In addition to the opcodes of the instruction states in the later chapter, which are used in class, the 3 opcodes are reserved for internal use in the Java machine implementation. For an instruction set of the Java machine is extended in the future, these are reserved opcodes. 2 of the reserved opcodes are numbers and the mnemonics, whatever. Alright, so okay. Not mind directly Java to the machine code has been already loaded, whatever. Okay, we're kind of looking for what the length of the actual ID is. I feel like it's 1 byte of code. Appropriate type arguments to the operand stack at the local table. The wide operands considered. In the code array, code length must be less than that. Wait, what? Let me actually check something. So 2 to the power of 32 is this number, and 2 to the power of 16 is I have a few questions, right? So why do you have the code length be such, as in it's a 4-byte integer, but in reality it has the capacity of a 16-byte integer, a 16-bit integer. So it's a 4-bit integer, but it has the capacity of a 16-bit one, 16-bit one or 2-byte one. So 4 bytes, it has the capacity of 2. Why? No clue. Honestly. Okay. At the next 0, to implement instruction opcode. Do we have to accept that opcode has a value that constraints opcode? Any opcode information? Number of dimensions that is limited to 255 by the size and dimension of dimensions opcode. I guess we can Java bytecode operand size, opcode size, 1 byte. I guess, sure, we can expect that it's 1 byte. So how about we actually start parsing some stuff? Right, that would be kind of cool. Parsing and visualizing some code. Alright, let's actually do that, right? So now the code block is actually consistent of some opcodes, right? Which the opcodes are actually going to be their own enum probably. Opcodes. Or probably operand. Opcode. Oh yes, just kind of instruction maybe. Right, they state that it's an instruction, right? And I have different types of instructions. And now instead of this being just empty thing of bytes, we could probably just do something like, okay, make it an array of instructions, right? And then we can actually bind the opcodes to certain integers, right? Like what we did before. Right, so let's see here. So how about we do that actually? Yeah. So now we have actually instruction, which should be implemented like so. Instruction, right? And we could do fn from bytes, which is going to take in the mutable vector of u8, right? And it's going to return a self, like most other functions from bytes. And then we can actually have something like, we have the tag, right? So I guess opcode, and that's going to be read u8 bytes, right? And that's the opcode. And then we can match opcode, and that opcode is going to be what? So by default it should actually probably say something like unhandled opcode, right? So panic unhandled opcode, and then we can print it in hex maybe. Was this how you print it in hex? I'm not quite sure. Let's actually do that and an opcode, right? So we have code, right? And now we can actually have like code bytes, which are going to be read bytes of the normal bytes, and how much? This much. And now instead of doing this, we can do for in 0 to how much code length, I guess, while code bytes length is more than 0. And that's going to be just block.code.push the instruction from bytes, right? And that's going to be readable code bytes, right? This time it's code bytes, and that's it, right? So that's probably going to come with a lot of errors, but no, actually, the only real error was this, which is easily fixable. CLS, I guess. Unhandled opcodes 2a. Let's actually do something like 0x CLS, and it's just at warning unreachable code. On by default, it doesn't matter. Okay, so we have 0x20, and what opcode? We can go back to here and we can just do this, right? So the first opcode is actually going to be 0x20a, which is a load. Okay, so the a load 0 should be okay. So we have a load and then some sort of count, right? So we have a load 0 all the way to a load 3, and we're going to check out its purpose after we've parsed it, right? So let's do something like a load And probably a load is probably going to have like, I guess, count maybe, because it doesn't matter, right? At the end of the day, it doesn't really matter. We want just to have a little bit of like, we want to make it easier for us to do, like, expand this out, and probably even, I don't know, make a virtual machine out of this. So we have a load 0, a load 0, a load 0, right? So that's a load 1, 2, and 3. So that's 0x to B, C, and D. And what do you do? Oh, in this case, we can just do some like, first, let's append this. So that's opcode underscore that, and then you just do opcode underscore a load 0. And what is that going to do? That's going to just return you self a load and how much? 0. Count 0. And let's copy this. Let's do 1, 2, and 3. Right. So why am I implementing all these? Because they're easy to implement, right? As my last advice suggested. So these are all similar instructions, right? They do the exact same thing. Why not just combine them together? They're just different opcodes. I don't see a reason why once I'm implementing this instruction, I can't just implement all of these opcodes, right? Because it's one instruction, multiple opcodes. Kind of like what you would do in a virtual machine, right? Once you reached, like, for example, some sort of instruction, right? Once you reach that instruction, I feel like you should just kind of implement all of the opcodes for one instruction. Make sense? Because then it would be a lot better to do that rather than, like, take the advice from last episode of implementing one instruction at a time, but then expand it to also implement one instruction at a time, but try to implement as many opcodes as you can, because opcodes are kind of like sometimes you have a lot of similar opcodes. Like, for example, in this case we have just the different amount of parameters, right? And that's just how you should do it, right? You should just take these opcodes and be like, okay, they do the exact same thing, just with different count, right? Why not save myself some time? Instead of having to match these opcodes, let's transform them into an instruction that does the exact same thing for all 4 of them, right? And now you have to implement just one functionality for all 4 of them, right? Yeah, that's it. So let's stop rambling about this and actually continue with the thing and actually start running. So a lot of mismatch types. Yeah, so the tag is actually going to be a U8, so it's easier to just do this, COS, and then run this again. I guess, yeah, sure. I kind of know that that's something I should do. Still, how about we do this? So it's uppercase. Uppercase should probably be for constant, right? So help convert identifier to uppercase. I don't know. No, that's no. Let's go to 0. Let's actually allow non-camel case. 178. Okay. So now we've reached the point where we're erroring at 0xb7. So what is that? That invokes special, right? It's interesting. So let's kind of do that, right? So let's do constant opcode invoke special u8 equal to this, and then you just have invoke special, and that's it. It has nothing, but it's, yeah, it's thing. Invoke special, that's just self invoke special. Also, right, so if you're designing, you could also just leave this like so, or you could do this, right? Most of the time I prefer using a struct because I sometimes migrate my code over to using structures instead of tuples. Like this fills up, and instead of an evoke special, it's now a U8 and a U8 and a U8 and a U8, and then I collapse this down into its own structure that's called something like, right, we have A U8, B U8, C U8, D U8, right? So now I have its own separate structure. I really like to just put it at the start because I don't need to do any more refactoring, right? It's easier this way. And also, if it has even more stuff that it has to do, I would probably add more to it. But it seems like this is just one invoke special, right? It doesn't matter. So we can just return this there, like so. It's empty. And then we have opcode 00. Are you sure? Okay. Index byte, invoke special. Operand stack. Okay, what's the let me actually check back on a load 0. Right, the operand stack is just the object reference. Something is wrong because I don't think 0x0 is called a no-op, and I don't think it's that. So maybe, right, invoke special and invoke special. Right, invoke special has a bunch of arguments in the operand stack for index byte 1, index byte 2. Format, does the format describe, like, for example, a load n, right? We do, right? So a load, right, what does it say? So it's the format is just a load n. Okay, and then the operand stack is the other stuff. So maybe, I'm not sure, right? Maybe it's actually invoke special invoke interface instance method special handling for superclasses, private, and instance initialization for methods. It's index byte, so that's index byte 1. Maybe it's this IB2, so let's actually do IB instead. So that's IB1 and IB2, which, sure, maybe that's how you should do it. I'm not sure. So that's read U8 bytes and read U8 bytes, and that's IB1 and IB2. Okay, run it again, and now we're erroring at 0xb1, so that's it. But I'm not sure, right? So maybe, I don't know. Okay, so we're hoping that this is correct, right? So next instruction is return. So constant opcode return, and then you do this, and then you just do return. So that's return. I guess you can just make underscore return, or maybe return underscore void, or you can just return, right? That doesn't matter. Opcode return, and that's going to be just self ret, right? And that's it. So that's our instruction. And next opcode, that's 0xb2. What is 0xb2? It's actually get static. So get static. Okay. Let's do get static, which is opcode get static u8 equal to this, right? And then you do get static, which would be get static, which is ib1, which is u8, ib2, u8. Where am I pulling this from? Here. See the format? Get static index byte, and then the other byte. So that's kind of cool. Okay, and then we can just do this and kind of copy this probably. Are used to construct an index. Why not just do, yeah, that's also used for in here. So it's index byte ib, I guess, maybe. Let's just do that because it seems like that's what it's doing. Right, it says in here they're constructing an index into the runtime constant pool. Right, that makes sense. Let's just do this. Let's be 16 bytes. That actually makes it a lot simpler, right? So this is going to be get static. So that's going to be invoke. That's going to be get static. Which again, it's get underscore static. For me personally, I like to do this. Okay, so now we have 0x12, which is LDC. So that's actually push runtime constant pool. IDC or LDC? Load constant. So that's LDC, right? So now we have LDC, constant opcode LDC, which is going to be U8, which is equal to this, right? So, and LDC is actually going to be what? It says just index. Is that it? So that's index is an unsigned byte, must be a valid. Okay, why is the documentation so weird? Right. So it's an index byte, which is a U16. I guess an index, so that's an ID. You can just call it an ID. Right, it's an ID, but it's 1 byte. So alright, I'm very much confused, right? But if that's what it says, then that's what I'm going to do. Right. If the documentation says that, I don't care. So ID is actually going to be equal to read U8 of bytes as U16, right? Does that make sense? That should make sense. Right, so that would be just reduce U8 as that. So that's an index into the unsigned byte must be a valid index in the runtime pool constant, and your index must be either the runtime constant int or a float. We can verify that afterwards. That doesn't matter. So then we have what other opcode do we have now? Well, the opcode is 0xb6, which is invoke virtual, right? So that invoke virtual is an ID of U16, right? It's invoking a virtual thingy. So that would be also const opcode of the invoke virtual. Virtual is a U8, and that's equal to, okay, that's 0xb6. Okay, so that's now opcode of invoke virtual, which would actually be a self virtual, invoke virtual. Again, it should probably be invoke underscore virtual because we're doing a little bit of other stuff. So that's ID, which is going to be a read U16 bytes, since they're basically saying, okay, we're constructing an index out of those 2 bytes. Okay, that's kind of cool. So now we can take this, okay, and then check for the next opcode, or we've finally parsed it. So let's actually see what we get, right? Let's actually go ahead and pipe this into debug.log once again. Open up our editor and edit the debug.log. Okay, so that's the code, which is a code block, and let's actually get the code. So that's get static load invoke virtual, then we have return. Right, that's it. So what does that mean really? Well, we're doing get static, which is something, I guess. Get static at index 2, which is do this. So that's get the system out method, right? That's what we're getting. So that's, yeah, system out. And what do? We load that. We load constant 3, so that's pushed onto the stack. Then we load constant 3, which is hello world. And then what do? We call invoke virtual on 4, which is print stream. Which, if we go into the documentation, by the way, for print stream got stream Java. If we go into the documentation for print stream, you would see, let's get this, right? We get the file and then the CSN. Right, that's it. Very simple. Okay, and now we probably, yeah, we got this. We got this parsed. That's basically all I really wanted to do for today. We got a basic debugger going. Debugger as in we can decode some instructions and we can see what they do. So again, if we take this a step further and actually print it correctly, you would see that get static would just get the system out. So that would just be the equivalent. Get static is the equivalent of doing system out, right? So that's system out. And then load would be loading this. That would just be hello world. So we basically push this, then we push this, which I guess maybe this is actually a method and that's calling it. I'm not quite sure. Maybe it's just standard out. So that's it. And then we do call to print stream, right? That's what we're doing. Essentially just system out, hello world, print stream. And then what do? We just return. Return from the function. That's it. And if we turn this into assembly, you would get push system out, push hello world, call print stream, and return. And that's literally it, right? That's literally it. So what can we do? Well, I guess for right now, not much, but we got at least logging working. And that was our goal for today, getting some logging working. So that's basically it for today. I hope you enjoyed the video. If you did, subscribe and like. Leave a comment for what we might do next with this, and maybe share it with a friend. And as for me, bye!